Now we're going to move on to the next section, which is on the cardinality of sets. Okay, this is towards the end of the semester. This class is one of my favorite. There's so much good stuff. Granted, this whole semester it's some of my favorite things, anyways. But at the end, especially, it just gets to some really cool topics. So we'd like to ask this question: how can we determine if two sets have the same size? In other words, the same number of elements, the same size. So let's consider these two sets here. We have set A, which consists of the elements A, B, C. And we have the set B, which consists of the elements 1, 2, 3. Do these have the same size? Well, an astute mathematician would be like, haha, yes. 1, 2, 3. And 1, 2, 3. Excellent. Good job. You did it. Okay. So yes, these two, not a trick question. But how we're going to formally define this is we could say, hey, there's kind of this buddy system. That this guy kind of has a buddy in that set. And this guy has a buddy in that set. And this one has a buddy in this set. So this is just a nice way, because now we can formally define this. We're going to say A and B have the same cardinality. So we're going to talk about cardinality. That's the size of these sets. They have the same cardinality if there exists a bijective function f that maps A to B. So we talked about bijective functions, right? That's a function that's going to be both surjective and injective, or both one-to-one and onto. You basically have this perfect matching that takes place between these. So if we can define a bijective function between two sets, they indeed have the same cardinality. They have the same size, or the same quote-unquote number of elements. So the notation that we're going to use in this class is A with this little squiggle, B. So I'll just call this A squiggle B is going to mean that they have the same cardinality. You might also see this notation of these vertical bars, almost like an absolute value. When you're referring to sets, sometimes the absolute value will refer to the number of elements in that. So the cardinality there. But we're just going to say two sets have the same cardinality if there's a squiggle between those. So some facts that we should know. If we look at a set A is going to have the same cardinality as itself, right? We should be able to create a bijective function from A to A, right? If I can map elements from A to itself, right, there's an easy pairing, there's this easy buddy system. We have this other statement that if A has the same cardinality as B, then B has the same cardinality of A. So formally then, if there exists a bijective function from A to B, there's also going to exist a bijective function from B to A, right? So you just go in the opposite direction of your pairing, right? Each buddy still has their same buddy, it's just which buddy gets mapped to which buddy. And this last one, if A has the same cardinality as B, and B has the same cardinality as C, then that means that A has the same cardinality as C. So again, talking about bijective functions, this should make sense. So you should be thinking, wait a minute, okay, I know where he's going, right? So you have it with itself, you have this in this direction, you also have this with the other direction, and then you have this AB, BC, then AC. Is this an equivalence relation, right? Because we're asking basically reflexive, symmetric, transitive. So if these three are all true, is this an equivalence relation? Well, remember, what is an equivalence relation? That says that you have an equivalence relation on a set where that set is going to refer to these elements then. So if there is, so what are we working with? What's our tools of making these statements? Well, these are talking about sets, right? So if we're talking about the set that this equivalence relation is on, well, I need to form a set which then consists of these sets. So if this is an equivalence relation, then the set that it's defined on would be the set of all sets. So maybe your brain hurts when you think about what is the set of all sets, right? So the set of all sets, that means that it's the set that then consists of all the sets. Okay, that's not too bad. We'll see what happens.